We're going to go ahead and work a couple problems of conservation of mechanical energy that involve some numbers. We're actually going to do some math. A 6,000 kilogram roller coaster travels along the path shown. The height at A is 150 meters, so they tell us this height, 150. The path A to C is frictionless, so we don't have to worry about anything changing mechanical energy here. The path C to D is not frictionless, so over here we do have some friction, which makes us a little bit sad. And then the coefficient of friction between the object and the surface from C to E is 0.6. So not only do we know that, but we know the coefficient of friction is equal to 0.6. Cool. How fast must the roller coaster be moving at A to just make it over the hill at C, which is 200 meters high? So we just got another couple pieces of information. They told us this height is 200 meters. They also told us that its velocity here is 0. It's just going to make it over the hill, so it's essentially at rest for a second at the top of that hill. Well, because it's frictionless, we know that the mechanical energy at A is equal to the mechanical energy at C. Now, we actually get to pick our zero height. And what I mean when I say our zero height is where are we measuring from. This is 150 meters off the ground, and this hill's 200 meters off the ground, but that might not be the most convenient thing to do. Maybe I want to make this my zero, because between these 2 points, all I care about is that this one's 50 meters higher. Now later we might have to deal with D, and that's actually going to mess with me if I'm up here. So I am going to go ahead and leave my 0 down here. My H0 is going to be the ground. However, it doesn't have to be the ground always. We can pick our 0 to be whatever we want, and I'll show you how that works out here in just a second. So first we're going to start with the mechanical energy at A. Well, that's mass times gravity times height at A plus mass times velocity at A squared, and remember kinetic energy is half mass times velocity, is equal to mass times gravity times height at C plus 1/2 mass times velocity at B, or not B, C squared. Now remember, if something's common to every term, it drops out. Mass is here and here and here and here. So I can go ahead and get rid of that. So now I have G times the height at A, which is 150 meters measured from the ground, plus 1/2 the velocity at A, which I don't know, that's what I'm trying to find, squared, is equal to G times the height at C, which we're told is 200 meters, plus 0, because the velocity at C we were told is 0. Now this is where I said we could pick our height to be the 150, we could call it 0, because if I subtract this G times 150 over, minus G times 150, minus G times 150, I see right away that my result is 1/2 the velocity at A squared is equal to G times 50, and that 50 is because it's only 50 meters above where it started. So if I had to pick this to be 0, then this would have been 50, and I'd have got the same answer. Okay? So 1/2 velocity at A squared is equal to G times 50. I'm going to go ahead and I'm going to multiply that both sides by 2, so the velocity at A squared is equal to 100 times G. So if I square root both sides, I have the velocity at A is equal to 10 times the square root of G, which is going to be right around 31.3 meters per second. So this roller coaster is moving at 31.3 meters per second as it leaves point A. Okay? That's the conservation of mechanical energy. Question B says, what is the height at B if the roller coaster has a velocity of 50 meters per second at B? Well, again, we can pick whatever we would like. Okay? Mechanical energy at B is going to be equal to the mechanical energy at C, which is also the mechanical energy at A. So it doesn't matter which one you pick. You're going to use the information you know about whichever point you pick to solve for stuff you don't know at B. So what I do know at B is its velocity. What I don't know is its height. So I'm going to say mass times gravity times the height at B plus 1/2 the mass times the velocity at B, which we're told squared, is equal to, and now it doesn't matter. I can pick A or I can pick C. I'm going to pick C because at C the velocity is 0, and that's one less thing I have to calculate. So that's 1/2 the mass times the velocity at C squared plus mass times gravity times height at C. MGHB, oh, mass is in this term and in this term and in this term and in this term, so there goes mass. So G times the height at B, which I don't know, G times the height at B, plus 1/2 times the velocity at b squared, which I do know is 50 squared, equals 1/2 the velocity at c squared, which is 0, plus g times the height at c, which we know is 200 meters. So I'm just going to go ahead and move over the stuff I know. G times the height at b is equal to g times 200 minus 1/2 of 50 squared. Okay. And then so I can divide everything by g, and I get the height at b is equal to g times 200, which is 1960, minus 1/2 50 squared. 50 squared is 2,500, and half of that is 1250, divided by 9.8. So this is equal to 710 divided by 9.8, and that's going to be right around 72.4 meters. So we see the height at B is 72.4 meters. We should stop and make sure that makes sense. Does it make sense that this is 72 meters high? Well, it's lower than this point, it's lower than that point. Yeah, that number does make sense. Okay. C, what is the work done by friction along the path C to D if the velocity of the roller coaster at D is 50 meters per second? This is a little bit different because now we have friction doing work, and that means our mechanical energy is going to go down. So now we actually have to account for that. So the mechanical energy at C plus the work done by friction is equal to the mechanical energy at D. Remember, if there's other things doing work, we just have to include that in our conservation of energy equation. Well, the mechanical energy at C is 1/2 mass times the velocity at c squared plus mgh at c plus the work done by friction is equal to the mechanical energy at D, which is 1/2 mass times the velocity at d squared plus mg times the height at D. Now if we go look at our picture, we can see that D is on the ground, so its potential energy is 0, which is nice. That's why we picked our height to be there, because we knew we were going to have to deal with that point. We also know that the velocity at C is 0, so that drops out. So what I'm left with is mass times G times the height at C, which we were told earlier is 200, plus the work done by friction is equal to 1/2 times the mass times the velocity at D squared, and they tell us that it's 50, so 1/2 mass times the velocity at D squared is 50 squared, plus the height at, okay, that's gone. Now, in the past, we've gone ahead and canceled the mass because it's been every term, but it's not anymore. The work done by friction does not include mass, so I can't cancel that out. So I'm actually going to have to deal with that. But before I do, I'm going to go ahead and add stuff over and combine my terms. So I have the work done by friction is equal to 1/2 mv squared right here. Well, 50 squared is 2,500, and half of that is 1250, so I have 1250 m minus, and let's see, G is 9.8. 9.8 times 200 is 1960, so 1960 m, and this looks familiar. This is equal to negative 710 times the mass, which we were told up above is 6,000 kilograms. This is going to be a really big number, 4,260,000 joules. Okay. Friction does negative 4,260,000 joules of work, bringing this roller coaster to a rest. That seems like a huge number, but a joule of energy is not a whole bunch of energy, so a joule of work, not a whole bunch of work. Granted, a 6,000 kilogram roller coaster is going to take quite a lot to stop, which I think is actually our next question. What is the average frictional force along the path C to D if the distance along the path is 400 meters? Well, remember, work done is equal to force times distance, but it's also equal to our change in energy. Okay? So, well, I don't know that we need our change in energy for this, but we do know that the work done by friction was 4,260,000 joules. So I have 4,260,000 is equal to the force, which I don't know, times the distance, 400 meters. I can divide both sides by 400 and come up with the force. So 4,260,000 divided by 400 is 10,650 newtons. So F equals 10,650 newtons of force, which is quite a lot of force. E says, how far is it from D to E if the roller coaster stops at E? Well, I'm going to draw a free body diagram and see what we got. We've got a roller coaster here. This is our roller coaster. This is point D. This is point E. We know that at D it's moving at 50 meters per second. We know here it's moving 0. We know the coefficient of friction is 0.6, and we know the normal force can be calculated off Fg because this is a flat level section. So the frictional force, Fs, and it is static friction because we're assuming the wheels are rolling, not sliding along the ground, is equal to the coefficient of static friction, 0.6, times the normal force, but since there's no other forces except gravity, this is mg, and that is going to be equal to, or times the distance. Okay, so work equals force times distance, so Fs times x is equal to its change in kinetic energy, right? Because work done equals change in kinetic energy. Well, its change in kinetic energy is 1/2 mass times velocity squared, final minus initial. Its final is 0, its initial is 50 meters per second, so 1/2 m times 50. And if I go ahead and make this substitution, I see 0.6 times m times g equals 1/2 m times 50 squared. That's our change in kinetic energy. Mass is in both sides again, so I can go ahead and cancel that. 0.6 times 9.8 gives me the left side, so 5.88 equals, sorry, I lost my x. 5.88x equals 1250. That's 50 squared divided by 2. So I'm going to take my 1250, divide it by 5.88, and I see 212.6. X equals 212.6 meters. So that's how far it takes it to stop. Now, F is an interesting question. F says, what's the fastest the roller coaster could be going at D if the distance from D to E is 150 meters? Okay, well, if the fastest it can be going at D, so it stops in 150 meters, that means 150 times 0.6, our coefficient of friction, times 9.88, or sorry, 9.8 g. So this is the static frictional force times the distance is equal to, and technically mass is in here, is equal to the change in kinetic energy, which is 1/2 mass times velocity squared. But again, our masses are going to cancel. So I have 150 times 0.6 times 9.8 is equal to 1/2 v squared, and I can solve this for v. So 5.88 times 150 is equal to 882, and if I multiply that by 2 and square root it, then what we see is the fastest that it can be going is 42 meters per second. If it's going faster than that, then our track isn't long enough and it is not going to stop. So the conservation of energy and mechanical energy work equations actually are pretty powerful and allow you to do some math that we used to rely on the kinematic equations to do, and you'd had to do lots of substitutions. But this allows you to do it in terms of force and distance and energy.